Pleasure to be here. Just-in-time delivery, absolutely. All my complex travel plans for this week almost completely unraveled. It's not, the microphone's not working. Right there. No, all my travel plans almost completely unraveled today, and today was the simple day. I've come in from South Africa, London, STFC Council. So yes, anyway, but I'm glad to be here, glad I could make it. Yes, I'm going to talk a bit about proton decay. This is very much a personal story, personal reflections of actually how I saw the field grow with Don's leadership through proton decay, but actually how that then connected to neutrino oscillations. Now, I'm not going to talk about the physics results of neutrino oscillations because we have a presentation after this. This great picture here is the Sudan 1 detector in its full glory. Didn't run for very long, you can probably see why. But you can see these three gentlemen here. So in front, it's Tom Fields from Argonne National Laboratory, Marvin Marshak from University of Minnesota. In the back, a very suspicious-looking gentleman inspecting the hardware and not looking very happy, actually, in that picture. But that really was the start of that journey. So this is very much a personal reflection. I'm not going to go too deeply into the science. Most people in here know the science, but what I want to do is put this in a historical perspective of how the search for proton decay actually shaped much of neutrino physics today. And of course, Don was a leading figure in this area. Actually, one of the pleasures of putting this presentation together, just-in-time delivery, 4 o'clock this morning, was actually reading, although I read some of the papers last night, was actually reading some of the earlier papers, papers I hadn't picked up for 40 years, and it was quite fascinating. Right, so why am I here? The first answer is obvious. Proton lifetime is longer than the lifetime of the universe. That is actually quite useful. So it's a useful property. That's not really what I meant. I started my DPhil here back in 1985, experimental particle physics at Oxford, and I decided to work on a proton decay experiment in Minnesota, underground and very cold. This is a picture I think Mark Lancaster dug out from the Rowell Summer School that year. I don't know if there are any other people. No, I should take it. It's quite. Don't look. We'll get rid of that very quickly. But we did actually try. We did try to identify a few years ago. Tried to identify all of the faces and figure out where they were, and there were about 5 we didn't get. But so why did I go underground? And so going back to Don's point, what was the attraction with Sudan 2? For me, it was a small collaboration. It felt much more hands-on, the technology, the electronics, and actually we had a really, really great team at Oxford. And just to focus in, so that page is a page from my DPhil thesis that someone kindly dug out for me from the library at Oxford. But that's the collaboration. So it was a small collaboration, and the group at Oxford was also relatively small. Don, obviously an absolute key figure. John Cobb and Giles Barr are both on that collaboration. So it was a really nice small group, very tight-knit group, and that was part of the attraction. But actually, it was part of the science. Partly the science, and ultimately, this science was astroparticle physics or particle astrophysics, depending where you come from, before it was really a big thing. So it was a really interesting time to get involved in this area. You saw the field growing and it kind of gradually growing into what it is today. So proton decay in 1984 was a seriously hot topic. This paper, which is a fantastic, this was the paper I was reading actually last night. Proton decay experiments. It was in the annual review of nuclear and particle science. So it was obviously written by Don. It was really a very, very deep overview of the field, the theory, the experimental status back in 1984. I tried to remember what 1984 was like. I typed in what was hot in 1984. That wasn't a good idea. But then I looked at some more specific searches. I actually remember what else was hot. So this was music in 1984, and I'm sure we'll all agree, much better than music today. I think we're all of a sufficient generation that is probably true. But actually, again, it really took me back to what it was like to be in Oxford during those times. So why actually? I mean, this is more why proton decay was the hot topic. So if you look back to a long time ago, discovery of W and Z firmly established the gauge theory of the Standard Model, the electroweak sector of the Standard Model. So that's a big tick. Late 70s, early 80s, the SU3 gauge theory of QCD had also been kind of confirmed by experiment. And experimental data at the time, this is not the data from the time, this is a tidier plot. This suggested that the three main forces, the strengths of the three main forces converged at a scale, at that time, from Don's paper, it was 10 to the 14 GeV. Of course, you can change the models around and you get a slightly different answer. So there was a hint of grand unification. Then Georgi and Glashow actually brought these ideas together in the context of an SU5 grand unified theory. So you put the quarks and the leptons in the same multiplet structure, and you end up with a new force at the scale of unification, mediated by the imaginatively named, at the time, X and Y bosons. Very, very, very heavy, though. So obviously a consequence of this new theory was baryon number is not conserved if you have this theory, and the proton should decay. And again, I think in Don's article, actually, it was really interesting just to make that connection, because we kind of know that baryon number non-conservation is out there because we're here. There's matter left in the universe. So it is one of the three conditions, Sakharov conditions, necessary to actually have matter left over in the universe from the Big Bang. So this is a really nice convergence of experimental data, hinting at unification and connecting to deeper symmetries. So that's why it was, I think, a really hot topic. Again, I like these old diagrams. These aren't made with latex packages, as you can tell. These look like they were hand-drawn. So simple SU5 grand unified theory. This is the underlying proton decay process. It's not the only one. There are others. You can always draw Higgs bosons in there or whatever you want. But basically, it's the process UD goes to X, producing a charged lepton and an antiquark. And you can see the final state here. You'll end up with the antiquark combining with the quark, and you end up with a charged lepton and a neutral meson. Doesn't have to be the pi, it can be others. Of course, the pi zero will then decay. So that's one final state. There are other models. They were available, and they still are available. So if you become supersymmetric, if that's the way you wish to go, they tend to predict the final state lepton to be a neutrino, typically an anti-tau neutrino. So one of the favoured decay modes there was P to K plus anti-tau neutrino. Now you can immediately see that these two topologies are very, very different. One is very, very light relativistic particles, which interact electromagnetically, and the other decay is a single hadronically interacting particle that will decay. So the signatures are very, very different. That does work. You can then start to actually just take the grand unified theories and actually start to use simple dimensional arguments to try and figure out what the lifetime of the proton should be. So this equation, a very simple equation, probably the only equation in here actually. So you've got the very, very heavy gauge boson to the power 4, so that's just the propagator term. You've got the strength of the grand unified coupling on the top, and on the bottom, and on the bottom you've also got the mass of the proton to the fifth power, so that's just phase space. And then you've got the usual kind of fudge factor A, which will take to be of order 1. You put the numbers in, and you get out the proton lifetime should be typically something like, or at least, it should be greater than or equal to 10 to the 31 years. So out of this theory, you get a very, very long proton lifetime, which again is consistent with observation. Now the experimental challenge, and it is a real experimental challenge, you're looking for signatures which are quite low energy, because obviously the energy scales that, is the proton mass, and you're looking for proton decay with lifetimes of 10 to the 31. The easy thing to do, if you could do it, would just be watch one proton. That would be a nice signature, so you'd see it decay. Not very practical and actually not very interesting at all. Or you can take roughly 10 to the 31 protons and watch them for a few years. And the challenge then is actually getting together 10 to the 31 protons or more, quite a large volume, and actually seeing a single decay, a fairly low energy decay in that huge volume. That's the experimental challenge. So you're going to look at maybe a 1,000-ton detector, and within that detector, one of those protons goes pop, you want to see it. So very, very challenging. So two distinct signatures drove two different approaches. So the electromagnetic approach gives you, the SU5 decay, E plus pi 0, where the pi 0 then decays to two photons. You have relativistic electromagnetically interacting particles. And in the other case, you have a slow kaon, which then decays. So there were two experimental approaches, basically based on those two signatures. So a really good way to be able to actually take a very large volume of material and see a signature of a single decay is just use water and look at the Cherenkov radiation, as we now do in the very large neutrino experiments. So this was pursued by the IMB detector in the US. This is a diagram actually from one of the papers. I think it shows perhaps progress in our representation of our detectors. Those dots are photomultiplier tubes. If Don was here today, he would be actually horrified because I did find a mistake in his paper. It wasn't he wrote not IMB, it was IBM. And he wouldn't have liked that anyway. But so this is a detector in the US. And of course, then there was the Kamioka nucleon decay experiment in Japan. So now known as Kamiokande, but the NDE is nucleon decay experiment. That's what it was designed for. There were also tracking calorimeters. So these were typically mixes of steel planes, drift tubes. Protons sit in the steel. When they decay, they cross the drift tubes, and you see a signature. I'll talk about Sudan too in a minute. So that was the experimental approach. The challenge, you're looking for a single proton decay, or just a handful if you want to make that discovery. Very, very big detector. I like this diagram because it was quite dated. There's a plane flying there. But anyway, you're looking at a very, very large detector. So cosmic ray-induced background is a problem. So if you have lots of neutrons flying around from spallation, they can fake a signature. They can bump into something in your detector, and you'll get a signature that could fake a proton decay. So you go deep underground, and that's fine. But you're always left with atmospheric neutrinos. You can't get away from the atmospheric neutrinos. So I think these proton decay experiments actually changed particle physics. Firstly, they were large underground experiments, and really very large at the time. And they were sensitive to the otherwise not very interesting neutrino-induced backgrounds. Not very interesting at the time, perhaps. Now we know that's not the case. So these experiments, I think, really did change the way we've been doing physics over the last years. I made a mistake in the slides, which I spotted 10 minutes ago. Just stepping forward a few years, I just got this quote. It's just a quote from a conference paper. I thought it was really interesting just because it links to one of the messages I want to get out at the end. So this is the situation in 1986. 5 experiments, Kolar, USEX, Frazier, IMB, and Kamiokande, designed to discover nucleon decay all around the world, well, Northern Hemisphere. 1 experiment is being constructed, Sudan 2, and 2 others are under serious discussions, Super Kamiokande, ultimately, obviously, a very, very important experiment in neutrino physics, and proton decay, actually, and Icarus. And obviously, just noting, nucleon decay had not been discovered at that time. But I think it's really interesting. These are familiar to techniques. The red ones, apart from Super Kamiokande, which is actually made from water, the red ones are tracking calorimeters. They evolved to the Minos experiment, which I'll talk about. The water Cherenkov detectors, Super Kamiokande, that is now, Kamiokande evolved into Super Kamiokande, and now, of course, Hyper Kamiokande. And the new one on the block was Icarus, which was the first large-scale liquid argon TPC. And of course, that's had a longer gestation period, but that's now evolving into the DUNE, deep underground neutrino experiment technology. So you can even back in 1986, you can see foresight of what might come in the future. Right, a few words about Sudan 2, my DPhil thesis. So I say this is quite a personal reflection. Deepest, darkest Minnesota, and that really is deepest, darkest Minnesota. The nearest large town, Ely, Minnesota, not Ely, Cambridgeshire. It was really interesting. When I was choosing projects, I had these were the main options that were on offer. Others were on offer as well. Zeus at Daisy, that had lots of advantages, and I can see many Zeus colleagues here. Hamburg nightlife being one of them. Certainly, I think the students who went there enjoyed that. Delphi at CERN on the Large Electron Positron Collider, mountains and skiing. I actually put that off for a few years, but I got there in the end. And then Sudan 2 in Minnesota. Lots of snow, no skiing, no mountains. I finally remember what it was. 3-2 beer. So this is basically low alcohol beer was all you could get in the state of Minnesota at the time. But actually, a really great and interesting group of scientists, and that's obviously the attraction, including Don. And I just saw Roger's looking at me there. It's not saying that there weren't great and interesting scientists in the other experiments. Of course, there were, but it was, as I say earlier, it was part of the attraction. So that's why I did it. I think by modern day standards, you look at a picture. This is a very blurry photograph of the detector. This was during the installation construction period. It doesn't look super high tech, but it did actually work incredibly well. It's a half a mile underground. You would go down the mine cage. So many of us go down. Have been down lots of different mine cages. I think this is one of the more fun ones. No lights, lots of bats flying around your head. They rushed up from the caverns underground. So it was always an interesting experience getting down. So how did it actually work? So this parchment picture, I took a photograph of. The basic detector element was really quite simple. It's just a tube, 1.5 centimeter diameter resistive tube. Put an electric field around it. So what happens? Can I point up? No, I won't try and point up there. Particle crosses that drift region, ionizes the gas. The gas then, the ions drift along the field lines, and you get signatures on the wires at the end, the anodes, and you get an induced signal on the cathode planes. So every time a particle goes through one of these tubes, you get an electronic blip. And then, of course, what you do is you sandwich all those tubes into a corrugated honeycomb structure. This is a picture. Even looking at that picture, this must have been a bad module or something. It doesn't look very well aligned, actually. But of course, it's the steel that provides all the protons. So if one of those protons in that steel decays, particles will come out, cross the gas, and you'll get signatures. So actually a very simple principle, but very effective. So actually, what you end up doing is you put these tubes in modules. I think there were 256. Yes, there were 256 of them, making up about a kiloton of mass. And that's the detector in its full glory. Clearly not taken with a modern camera, but say pretty simple technique. But you have to have simple techniques because you need very large, massive detectors. So simplicity actually is a real benefit. So Sudan 2 was designed to study proton decay. That's why it was designed. In some ways, it's actually a really beautiful detector. It's a very large volume, and you have voxels, like pixels, but three-dimensional pixels, roughly a cubic centimeter. So that's your resolution for particles. You have very low thresholds, gas detection, and because you're ionizing the gas, you actually get good particle ID as well, and you could then make projective 3D images. So these were an example of some of the event displays, just to give you a sense of what the events in this detector looked like. So you got the tracks, you measured the tracks, saw what happened to them as they scattered in the medium. What about the results? Well, I think everybody knows proton decay hasn't been discovered yet, so Sudan 2 did not discover proton decay. One of the advantages of this is you could look at many different decay topologies because you saw the topology. All of the channels had some level of expected neutrino background. And I mean, Giles, who was just sitting in front of where I sat down earlier, he was working on these analyses for a number of years, and the neutrino backgrounds were absolutely key. And through Giles, the Oxford group actually played a very significant role in actually tuning the simulations of atmospheric neutrinos and cosmic ray showers and production of neutrinos. The bottom line was what was seen in the experiment was consistent with these backgrounds. So the most stringent lifetime limit from Sudan 2 was a very long time, 6 times 10 to the 32 years. But if you look at if you also then compare that, so that is actually a pretty impressive result. Today's best limits come from the Super Kamiokande experiment. Water is very scalable. You can make, as long as light propagates through that water, and you've got enough money to pay for the multipliers, you can scale it. So very, very large detector, very large fiducial mass. And now the current lifetime limits are up at 10 to the 34 years. So the proton decay, so the legacy. One of the things I really enjoyed about being in Oxford back in the late 80s was actually discussions over coffee. There was a very active culture of meeting up with colleagues over coffee, not talking about football, actually talking about physics. So obviously myself and John, who I saw up there, Don Perkins, sometimes it got livened up by Mike Bowler chipping in. Some of the discussions, certainly with John, looked a bit like that, but I was hoping John was going to be here today. But actually the discussions were great, and it was really physics. We talked about proton decay. Obviously Don had his passion for cosmic ray physics, so we actually talked about cosmic ray physics, and my thesis was actually more connected to cosmic ray physics than proton decay. But actually, we started talking more and more about neutrinos and neutrino oscillations. And really, because at this time, the solar neutrino puzzle was out there, but actually also these proton decay experiments were starting to see anomalies. Not all of them. Some of them saw things that were consistent with the standard non-oscillating predictions, but others were showing hints. So we were starting to see hints that the background for proton decay was actually the signal for something else we now know is extremely, extremely interesting. So what I think, and I will actually, because I'm going to argue this, I think you could argue that Sudan 2 seeded what is now a very, very strong UK neutrino activity with Fermilab in parallel with a very strong collaboration with Japan. So members of the Sudan 2 collaboration, they were actually key in the development of the concept of P875, I hope I've got the number right, a long baseline neutrino oscillation experiment at Fermilab. And this ultimately resulted in the formation of the Minos collaboration. I think that was helped, I'm not sure that's the right word, by the demise of the SSC in 1993, which actually really made the collaboration very strong. So Stan there was one of the leading figures in the development of the proposal and the experiment. It also turned out that if you start at Fermilab, the Sudan mine is about 730 miles away. That turns out to be just about the right distance, not perfect, but to study neutrino oscillations for muon neutrinos. You've got to go underground again, so you go back to the Sudan mine. So this was a second generation long-time neutrino oscillation experiment. I'm not going to go into the details here in great detail, but the basic idea is you go to Fermilab, you've got a nice accelerator complex, you smash 120 GeV protons into a target, create a beam of neutrinos, they fly across, well actually under the Midwest, under Lake Superior, and then you detect those neutrinos with big detectors. One of them you put right near the source, and then one of them you put down the mine. So that's the basic experiment. Then you compare what you see close to the source and a long way away, and if they're different, something's happened to the neutrinos. They've oscillated. And I think Paul will say more about that in his presentation. Again, these detectors were actually fairly simple. If you compare these to the LHC or even the large electron positron collider detectors, these are pretty simple, and they're simple because the thing you're aiming for is mass. You need to get a lot of mass in your detector. So this is the detector. Basically, it's planes of steel interlayered with scintillator, so 484 1-inch thick steel planes with 1 centimetre scintillator in between. Somewhat similar to the Sudan idea, all of your protons live in, well, most of your protons live in steel. If something decays, it will cross some scintillator, give a flash of scintillation light, and then you read it out. So you get a signal, in this case in PMTs. So lots of layers. Just to give you a sense, that little bit of plastic at the bottom, that is the basic detector, detecting element, and then you have put a bung of PMT on the end of it. That's 4 centimeters wide, so it's pretty coarse, pretty crude. And it could be because the physics was a high enough energy that the muons that were produced traversed quite a long time in the detector. And you can see cameras are getting better. So this is a picture of the Minos detector. It's filling the hall. So it was actually, I mean, this was actually a really, again, a simple detector, but actually a really interesting experiment. And all of the challenges were obviously understanding systematics. I won't say too much more about that, the actual experiment itself. But I think the UK, I really want to emphasize, the UK was a very, very big player in Sudan too. So big player in Minos. And a lot of that came out of those collaborations we built in the Sudan 2 collaboration with Don kind of in the fore there. So for Minos, Sudan 2 collaborators were joined, Oxford and RAL, were joined by Sussex and UCL, and then when I returned from my sabbatical from neutrinos, so my time at CERN, I came to Cambridge, then Cambridge joined Minos. And again, I think at this time, what we were seeing is a shift in the physics landscape in the UK. So T to K was out there as well. So we were seeing a real rapid growth of neutrino physics in the UK. And again, I think just to give you a sense, this map, I like this little map. The UK was a really big part of I mean, it was the US, largest part of the collaboration was the US, but the UK was a significant contributor. But again, a rather small experiment. Right, just coming to an end. So I'm now thinking about what's the legacy of Minos and Sudan, 1 and 2. I think the engagement of the UK in Minos, and it was a strong engagement from quite a large community, and then the UK's involvement in the future US neutrino program, underpinned that engagement in the future, which still future. So I was trying to think about. This was only 10 years ago, but it feels like a long time. So around 2013, a few of us, including colleagues in Oxford, were actually starting to look beyond Minos. What do we want to do next? Obviously, we had a strong connection with Fermilab. We'd built that. And in fact, Giles and myself started to get interested in liquid argon, the liquid argon TPC program. I hope I got the dates right, but Oxford and Cambridge actually joined that liquid argon program. I think it was 2013. Giles is nodding. Yeah, I think it was. And then, and that was partly because the experiment actually is a really interesting experiment and the technology is fascinating. But then we formed a Deep Underground Neutrino Experiment Consortium in the UK. 2015, I was elected as one of the first co-spokespersons. And very rapidly, we actually got money out of government, which is still, I shouldn't say I'm amazed that happened. I'm not amazed, actually. We had a very, very strong science case. And part of this was actually really, I think part of what helped is Joe Johnson, the minister then, Boris's brother, signed the UK-US Science and Technology Collaboration Framework. And at that time, the first thing under that framework he announced was the UK investment in LBNF DUNE. So today, the UK is really a really big player in the $3 billion LBNF DUNE project. The UK is not putting in $3 billion, by the way. So actually, along with Hyper-K and other investments, including things like microboom, neutrino physics in the UK is really looking incredibly exciting now. So I think that's just, you can almost trace back some of these connections right back to Sudan 1. Just in case people don't know what DUNE is, I've got 2 slides. It's very similar to Minos, big neutrino beam, very high power, 1, 2 megawatt class neutrino beam. This time fired at a very deep mine in South Dakota. But the key here is it's big. It's very, very big. This picture here is one of the 4 large caverns that has just been excavated. You can see a digging machine at that back. That little yellow thing is a digging machine. These caverns are absolutely enormous. Hopefully, ultimately, each of these caverns is going to host a cryostat with 17,000 tons of liquid argon. Trying to picture, it's probably, let's pretend it's the size of this lecture theatre. Actually, it's probably a bit bigger than that. Fill it with liquid argon, and if anything happens in that liquid argon, you see it in intricate detail. I mean, this is a beautiful, challenging technology, but a beautiful technology. So imagine you've got all your protons sitting in your argon, one of them goes pop, you'll get images like that. So impressive. This is actually from the prototype of one of the DUNE experiments operating at CERN at the moment. So, final slide really. So what are the physics headlines? Why are we doing this big project? Firstly, it's the origin of matter. Why is the matter dominance over antimatter? Determine the mass hierarchy, discover CP violation. Second one is unification of forces. Search for and hopefully discover proton decay. So actually we're coming back full circle. Now we're building a big detector to do neutrinos. Perhaps the opposite will happen than what happened before. We'll actually get lucky and discover proton decay. That would be great. We'll see. And then, of course, there's a piece around neutrinos from galactic supernova. We're due one now. It's, 37 years ago since the last one. So maybe we'll get hints of really interesting astrophysical information about black hole formation. So those are the headlines. But I think it's really nice just to see proton decay is still on the agenda. The Hyperkamiya-Kandi physics case in Japan, again, has similar, not exactly the same science goals, but proton decay is one of them. A closing thought. I think these early proton decay experiments, the 2 on the left, they're quite, they look quite basic, look quite dated now. But actually, I think they had left a huge legacy in the UK. If we weren't involved in these experiments, probably at the right time, it's not clear how, what our program would look like today in the UK. So I think it's just an interesting reflection. And clearly, I mean, Don was a real big part of this story, driving forward the interest in proton decay in the UK right at the beginning. So I think just on that note, I will close. Maybe on time. It is on time.